Hello, everyone. Welcome back to the YouTube channel, An American Professor. In today's video, we're going to continue with the playlist for the basics and fundamentals of reinforcement learning. Today, I'm going to be discussing the state transition function in reinforcement learning. This is effectively our dynamics for the system we're trying to control. And the first question we need to ask ourselves is, what is the state transition function in reinforcement learning? In RL, the state transition function most generically defines the probability of an agent transitioning from one state to another, possibly including the influence of a control as part of the dynamics. The state transition function can be deterministic or stochastic. That is, the dynamics can be if you're in some state and you put in some control, you deterministically go to another state. That'd be deterministic dynamics. Another possibility is you're in one state and you input a control into the system and you end up in multiple states according to some probability distribution. That's an alternative set of dynamics. The state transition function, like I said, can be deterministic or stochastic. Keep that in mind. If the function is deterministic, then the agent will always transition to the same next state given the same current state and control. That is, if you return to a similar state from early on in an episode or training experience. If the state transition function is stochastic, then the agent may transition to different next states given the same current state and control, usually because of some kind of noise or disturbance in the environment. So let's dwell here on the state transition function. The state transition function and exploration are integrally linked. If the state transition function is deterministic, it is easier to learn the Q function for a fixed policy because the agent will always follow the same path and will not randomly enter next states. However, if the state transition function is stochastic, then the agent randomly explores new next states, and thus the agent requires much longer training time to learn the true Q function, corresponding to the fixed policy. Additionally, if the agent is updating its policy online using Q learning, it will take a longer time for the agent to learn the optimal Q function in an environment with stochastic dynamics rather than deterministic dynamics. The state transition function specifies the behavior of a system in both deterministic and stochastic cases. In a deterministic system, the state transition function is used to determine the next state given the current state and control with probability 1, that is, with certainty. In a stochastic system, the state transition function encodes the probability of transitioning to each possible next state given the current state and control. For Markov decision processes, that is MDPs, the state transition probabilities under the influence of a control can be encoded into an n by n matrix for each control U, assuming a finite number of n states. With the state transition function encoded as a matrix in this manner, this enables simpler matrix vector operations for algorithms such as value iteration or policy iteration, for example. The specification of the state transition function is therefore important for both deterministic and stochastic systems. In RL, the state transition function is used to determine how the agent will move from one state to another, possibly under the influence of a control or some kind of environmental noise. The goal of the agent is to find a policy that maximizes its cumulative reward in a given environment. And the state transition function is one of the key factors in determining what the optimal policy will be. As such, it is important to understand how state transition functions work in order to develop effective RL algorithms. Other than MDPs, state transition functions are useful to model continuously changing state too. For MDPs, most often they are modeling discrete time and a finite number of states. However, one could apply the state transition function idea from RL to more general continuous state and continuous time using ideas from calculus. For example, one can model some environment using a system of ordinary differential equations, ODEs. And the state transition function here will be the right-hand side of the system of ODEs, usually written out in a factored form as AX plus BU. With this model, it is very simple to turn it into a discrete time system through sampling, but the state will be continuous still. In conclusion, a state transition function is a mathematical function that most generically calculates the probability of a system moving from one state to another under the influence of a control an agent is taking. It is most often deterministic, where the future state of the system is known with certainty. However, it can also be used in stochastic systems where one or multiple sources of noise are present. That is where the future state is not known with certainty given the present state and a present control. In either case, the state transition function can be used to calculate the likelihood of a certain transition occurring. The main advantage of using a state transition function is that it can provide valuable insights into the behavior of a system that is the one we're trying to control to minimize or maximize some objective function. For example, it can be used to determine the most likely path that a system will take. That is some state trajectory. However, there are some disadvantages to using a state transition function. One drawback is that the state transition function can be computationally expensive to evaluate when the number of discrete states is very large. In future articles, I will go into more depth on the mathematical details to make explicit the discussion here and provide some computationally engaging examples, ones that can be programmed using Python. That's it for this video. Don't forget to hit that like and subscribe button so you don't miss any more Python or reinforcement learning videos. Also, I encourage you to join Medium with this referral link here to stay up to date on my writing of Medium articles. Until next time, signing off.